Imagine something the size of a city, maybe 20 kilometers across, yet containing more mass than our entire sun. It is so dense that a single teaspoon of its material weighs roughly 1 billion tons. Gravity is pulling inward with a force so extreme that it has already crushed atoms themselves out of existence. Electrons have been shoved into protons. Matter has been compressed beyond anything you will ever encounter anywhere else in the observable universe. And yet, this object does not collapse into a black hole. Something is pushing back. Something inside this dead star is generating enough pressure to hold off the most violent gravitational crush in the cosmos. But here is what most people never think to ask. Where does that pressure actually come from? The atoms are gone. The electrons are gone. Normal physics has already failed. So what exactly is still resisting? Before we go any further, if you find this kind of deep exploration fascinating, a quick like or subscribe really helps the channel grow. It is a small thing for you, but it makes a huge difference for me. Also, before we begin, we're now live on Spotify. The link's in the description if you'd like to listen to us wherever you are. Now, let's begin. Let's start with something you already understand: pressure. You feel it every day. The air pressing on your skin right now is exerting about 14.5 pounds of force on every square inch of your body. You don't notice it because the pressure inside your body matches the pressure outside. But pressure is real. It is physical. It is what keeps a balloon inflated, what keeps the atmosphere from collapsing to the ground, what keeps the ocean from crushing a submarine at shallow depths. In a normal star like the Sun, pressure is what keeps the entire thing from falling in on itself. The Sun is enormous. It has a diameter of about 864,000 miles. It contains roughly 330,000 times the mass of Earth. All that mass is being pulled inward by gravity. Every layer of the Sun is being dragged toward the center by the combined gravitational pull of everything below it. The force is staggering. If nothing opposed it, the entire Sun would collapse to a point in less than an hour. But something does oppose it. Deep inside the Sun's core, temperatures reach about 27 million degrees Fahrenheit. At those temperatures, hydrogen nuclei move so fast that they overcome their electrical repulsion and slam together, fusing into helium. This is nuclear fusion, and it releases an extraordinary amount of energy. That energy heats the gas around it, making it expand outward, creating pressure, thermal pressure, radiation pressure, the outward push of hot, energetic matter resisting the inward pull of gravity. This balance between gravity pulling in and thermal pressure pushing out is called hydrostatic equilibrium. It is the reason the Sun exists as a stable, glowing sphere rather than collapsing or exploding. The Sun has maintained this balance for roughly 4.5 billion years. Every second, it converts about 600 million tons of hydrogen into helium, releasing energy equivalent to billions of nuclear bombs. And that energy, that heat, that outward push, is what holds the Sun up against its own immense weight. This is how every normal star works. Main sequence stars, the stars you see scattered across the night sky, are all doing the same thing, fusing lighter elements into heavier ones, releasing energy, generating thermal pressure, holding gravity at bay. It is a beautifully simple arrangement. Heat pushes out, gravity pulls in, and as long as there is fuel to burn, the star survives. But fuel runs out. Every star has a finite amount of hydrogen in its core. When that hydrogen is exhausted, the star begins to change. Massive stars can switch to fusing heavier elements: helium into carbon, carbon into neon, neon into oxygen, oxygen into silicon, silicon into iron. Each stage burns faster than the last. Hydrogen fusion in a massive star can last millions of years, Silicon fusion lasts about 1 day. And then the star reaches iron, and everything stops. Iron is the end of the line. When you fuse elements lighter than iron, you release energy. That is why fusion powers stars. But iron is different. Fusing iron does not release energy. It absorbs energy. It takes more energy to fuse iron than the process gives back. So when the core of a massive star fills with iron, it is like a fire running out of wood. The furnace goes dark. The thermal pressure that held the star up for millions of years vanishes, and gravity, which has been waiting patiently all along, wins. What happens next is catastrophic. The iron core, no longer supported by thermal pressure, collapses under its own weight. The collapse happens at roughly 1/4 the speed of light. Think about what that means. Material at the edge of the core, thousands of kilometers from the center, is falling inward at something like 70,000 kilometers per second. The entire core, a ball of iron roughly the size of Earth, is imploding in on itself faster than you can blink. In less than a single second, that Earth-sized core is compressed to something about 20 kilometers across. A volume that was once large enough to contain our entire planet is crushed down to the size of a city in a fraction of a heartbeat. During that fraction of a second, something strange happens at the center. The inner part of the core reaches nuclear density and suddenly stiffens. It cannot be compressed any further, at least not immediately. The material hitting this stiffened core bounces. A shock wave forms, racing outward through the still infalling layers like a wall of force pushing against the avalanche of matter still crashing down from above. But the shock wave is not strong enough on its own. It stalls. The weight of the material still falling inward is too great. For a brief, desperate moment, the shock wave sits there, stuck, losing energy, while matter continues to pile onto the core from above. And then the neutrinos arrive. During the collapse, the conversion of protons and electrons into neutrons produces an almost incomprehensible flood of neutrinos. Neutrinos are ghostly particles that barely interact with matter. Under normal circumstances, a neutrino can pass through a light year of solid lead without being absorbed. But the densities at the core of a collapsing star are so extreme that even neutrinos get partially trapped. They deposit a fraction of their energy into the stalled shockwave, and that fraction is enough. The shockwave revives. It begins ploughing outward through the outer layers of the star, accelerating, gaining strength, tearing the star apart from the inside out. The outer layers of the star, suddenly unsupported, come crashing down onto the collapsing core. They slam into the rebounding shockwave and are flung outward in a colossal explosion, a supernova, one of the most violent events in the universe. For a few weeks, a single exploding star can outshine an entire galaxy containing hundreds of billions of suns. The energy released in those few seconds of core collapse exceeds the total energy output of the Sun over its entire 10 billion year lifetime. Most of that energy is carried away by the neutrinos, invisible to the naked eye, but detectable by specialized instruments on Earth. The light and kinetic energy of the explosion, as spectacular as they are, represent only about 1% of the total energy released. The other 99% leaves as neutrinos, a silent, invisible torrent of particles streaming outward at nearly the speed of light. But the core survives. It doesn't get blown apart. Instead, it sits there in the aftermath, a tiny, ultra-dense remnant of what was once a star dozens of times more massive than the Sun. And this remnant is what we call a neutron star. Now, let's be very precise about what a neutron star actually is, because calling it a star is almost misleading. It is not burning anything. It is not fusing elements. It has no nuclear furnace. It produces no energy through any of the processes that define a normal star. It is a dead core, a stellar corpse, and it is one of the most extreme objects in the known universe. A typical neutron star has a mass of about 1.5 times the mass of the Sun. Some are closer to 2 solar masses. All that mass is compressed into a sphere roughly 20 kilometers across. That is about 12 miles, about the length of Manhattan Island. Think about that. Take a star more massive than the Sun, something that would normally span hundreds of thousands of miles, and compress it until it fits inside a single city. That is a neutron star. The density is beyond anything you have ever encountered. The average density of a neutron star is around 400 trillion grams per cubic centimeter. That is about 400 trillion times the density of water. If you scooped out a teaspoon of neutron star material and somehow brought it to Earth, that teaspoon would weigh roughly 1 billion tons. 1 billion tons in a volume smaller than your thumbnail. For comparison, the entire population of Earth, all 8 billion people combined, weighs roughly about 480 million tons. A single teaspoon of neutron star matter weighs more than twice the entire human race. The surface gravity on a neutron star is about 200 billion times stronger than the gravity you feel standing on Earth right now. If you dropped an object from a height of 1 meter above the surface of a neutron star, it would hit the surface in about 1/millionth of a second, traveling at roughly 7 million kilometers per hour. The escape velocity, the speed you would need to leave the surface, is about 100,000 to 150,000 kilometers per second. That is roughly 1/3 to half the speed of light, just to leave the surface. Nothing in your everyday experience comes anywhere close to these conditions. And the gravitational pressure at the center of a neutron star is something almost impossible to express in human terms. The weight of all that matter pressing inward creates pressures that reach into the trillions of pascals. Every layer pushes down on the layer beneath it, and the layers go deep. The center of a neutron star experiences a gravitational squeeze so powerful that it distorts not just matter, but space-time itself. General relativity becomes essential for understanding the structure. Newtonian gravity, the classical physics that works perfectly well for planets and everyday engineering, is not sufficient here. You need Einstein's equations to accurately describe how a neutron star holds together or fails to hold together. So here is the situation. You have a dead stellar core. There is no fusion. There is no heat source driving thermal pressure outward. The nuclear furnace that sustained the original star for millions of years is gone. Radiation pressure, the force exerted by photons streaming outward, is negligible at these densities. Thermal energy still exists inside the neutron star. Newly formed neutron stars can have surface temperatures of hundreds of thousands or even millions of degrees. But this heat contributes almost nothing to the pressure that holds the star up. The gravitational force is so overwhelmingly strong that thermal pressure is like trying to hold back an avalanche with a hand fan. It simply does not matter at this scale. This is the central paradox. In a normal star, the answer to the question of what holds it up is simple. Heat. Fusion generates energy, energy creates pressure, and pressure balances gravity. But in a neutron star, that mechanism is gone. There is no fusion. There is no radiation pressure worth mentioning. Thermal pressure is a rounding error compared to the gravitational forces involved. Every familiar source of pressure has been eliminated. And yet the neutron star does not collapse. Something is still pushing back. Something is generating enough outward pressure to resist gravity at a scale where gravity has already destroyed atoms themselves. That something is what this entire story is about. But before we get there, we need to understand just how thoroughly gravity has won inside a neutron star. Because the destruction is not partial, it is total. Every structure you think of as fundamental has been erased. Start with ordinary matter, the stuff you are made of, your body, the chair you are sitting on, the air in your lungs. All of it is made of atoms. An atom has a nucleus at its center, containing protons and neutrons packed together by the strong nuclear force. Surrounding that nucleus, at a relatively enormous distance, are electrons. Electrons are tiny compared to the nucleus. The nucleus contains over 99.9% of the atom's mass, but the electrons are what give atoms their size. The electron cloud determines how big an atom is, how atoms interact with each other, how chemistry works. Without electrons maintaining their orbits, atoms would be almost unimaginably smaller. In ordinary matter, atoms are mostly empty space. If you scaled a hydrogen atom so that the nucleus was the size of a marble, the single electron would be orbiting about a kilometer away. Everything in between is empty. This is the normal state of matter. It is how the universe works at room temperature and atmospheric pressure. Atoms maintain their structure, electrons stay in their orbits, and matter has the familiar properties you experience every day. Solidity, density, texture, all of it comes from atoms behaving normally. Inside a neutron star, none of this applies. The gravitational pressure is so extreme that atoms cannot exist. The electron clouds are the first to go. Under moderate compression, electrons are squeezed closer to the nucleus. This is what happens inside a white dwarf, the dense remnant of a smaller star. In a white dwarf, the atoms are compressed so tightly that electron clouds overlap. The matter becomes degenerate, a term we will explore much more deeply soon. But the nuclei remain intact. The protons and neutrons inside the nuclei are still distinct, still organized, still recognizable. A white dwarf is extremely dense, about 1,000,000 times denser than water, but it still contains identifiable atomic nuclei surrounded by a sea of electrons. A neutron star goes far beyond this. The pressure inside a neutron star is so high that even the nuclei themselves are destroyed. At densities exceeding about 400 billion grams per cubic centimeter, atomic nuclei begin to dissolve. The individual protons and neutrons that made up those nuclei are squeezed so close together that they lose their individual identities within nuclei. The boundaries between one nucleus and the next blur and vanish. There are no more atoms. There are no more distinct nuclei. There is just a continuous sea of particles, overwhelmingly neutrons, with a small fraction of protons and electrons mixed in. The electrons themselves undergo a transformation. At these extreme densities, the electrons have so much energy that they are captured by protons through a process called inverse beta decay. A proton absorbs an electron, and the two combine to form a neutron and a neutrino. The neutrino escapes. The neutron stays. This process is why neutron stars are called neutron stars. The overwhelming majority of the matter has been converted into neutrons. The process is relentless. As gravity squeezes harder, more electrons are forced into protons, creating more neutrons. The composition shifts until the material is roughly 95% neutrons and only about 5% protons and electrons. Think about what this means. In ordinary matter, the diversity of elements comes from different numbers of protons in the nucleus. Hydrogen has 1 proton. Carbon has 6. Iron has 26. Gold has 79. The periodic table, all the richness of chemistry, all the variety of materials and substances you see around you, all of it depends on atoms maintaining their structure. Inside a neutron star, all of that is gone. There is no chemistry. There are no elements. There is no periodic table. There is just an incomprehensibly dense fluid of neutrons, crushed together so tightly that they are practically touching. To appreciate how dense this is, consider that an atomic nucleus, the densest part of ordinary matter, has a density of about 230 trillion grams per cubic centimeter. The core of a neutron star reaches densities of roughly 5 to 10 times nuclear density. The matter inside is denser than the nucleus of an atom, denser than the densest thing that exists in ordinary matter. You are beyond the periodic table, beyond chemistry, beyond atomic structure entirely. And gravity is still pulling. It has not stopped. It has not paused to admire its handiwork. Every kilogram of material inside the neutron star is being pulled toward the center with a force that makes the surface gravity of the Sun look like a gentle suggestion. The gravitational acceleration at the surface is roughly 2 trillion meters per second squared. That is about 200 billion times Earth's 9.8. And it only gets stronger as you go deeper. At the center of the star, the pressure from all the surrounding mass pressing inward reaches values so extreme that they challenge the limits of nuclear physics. So let me be absolutely clear about what we are looking at. A neutron star is a ball of matter so compressed that atoms do not exist inside it. The electrons have been absorbed into the protons. The protons have been converted into neutrons. The nuclei have dissolved. The density exceeds that of atomic nuclei. The gravitational force is hundreds of billions of times stronger than on Earth. The escape velocity is a significant fraction of the speed of light. Space-time itself is noticeably curved. And there is no fusion, no fire, no heat engine driving any outward pressure. Every source of pressure you learned about in physics class has been eliminated. Let me close each door one at a time, so you can feel how completely the neutron star has been stripped of defenses. Gas pressure. In a normal gas, pressure comes from molecules bouncing around, colliding with each other and with the walls of their container. The faster they move, the harder they hit, the more pressure. This is the pressure that inflates a tire, that lifts the lid on a pot of boiling water. But gas pressure requires space between particles. It requires particles moving freely, bouncing off each other in random directions. Inside a neutron star, there is no space between particles. The neutrons are packed shoulder to shoulder, nucleus to nucleus, so tightly that there is no room for free bouncing. The concept of a freely moving gas particle does not apply here. Gas pressure is gone. Radiation pressure. In a normal star, photons generated by fusion stream outward from the core, pushing on the surrounding material like a constant wind of light. This radiation pressure contributes to holding the star up. But radiation pressure requires a source of photons. It requires an ongoing process generating light from the inside. A neutron star has no fusion. No nuclear reactions are producing photons in the core. There is no light source pushing outward. Radiation pressure is gone. Mechanical resistance. When you set a book on a table, the table does not collapse because the atoms in the table resist compression. The electron clouds of neighboring atoms repel each other electromagnetically. They push back. This electromagnetic resistance is the reason solid objects feel solid. It is the reason the ground holds you up. But mechanical resistance depends on atoms having electron clouds. It depends on the electromagnetic force operating between intact atoms. Inside a neutron star, there are no atoms. There are no electron clouds. The electrons have been absorbed. The electromagnetic structure that gives solid matter its rigidity does not exist here. Mechanical resistance is gone. Thermal pressure. Even without fusion, a hot object exerts pressure simply because its particles are moving. A neutron star is hot, especially a young one. Surface temperatures can reach millions of degrees. But at these densities, thermal pressure is negligible compared to the gravitational force. The gravity of a neutron star is so strong that even millions of degrees of heat contribute almost nothing to the structural support. It is like trying to prop up a skyscraper with a sheet of paper. Thermal pressure is irrelevant. Every door is closed. Every mechanism you might reach for to explain how this star survives has been eliminated by the sheer brutality of the gravitational compression. And yet the neutron star sits there, stable, intact, not collapsing further. It can spin hundreds of times per second, broadcasting beams of radiation across the galaxy. It can persist for billions of years, cooling slowly in the darkness of space, but never collapsing. Something is holding it up. This is the question that sits at the heart of some of the most extreme physics in the universe. It is not a question about stars in the usual sense. It is a question about what matter does when it is pushed to the absolute edge of existence. When you crush matter beyond atoms, beyond nuclei, beyond anything chemistry or ordinary physics can describe, what happens? Why does it stop? What force, what principle, what law of nature steps in at the last moment and says, no further? The answer does not come from thermodynamics. It does not come from ordinary mechanics. It does not come from any branch of classical physics. It comes from something far deeper, something built into the quantum structure of reality itself. The pressure that holds up a neutron star is not generated by heat or motion in the usual sense. It is generated by the fundamental nature of the particles that make up the star. And to understand it, we are going to have to go deep into quantum mechanics, into the bizarre rules that govern how identical particles behave when they are forced into impossibly tight spaces. Because here is the remarkable thing. The neutron star should collapse. By every classical argument, there is nothing stopping it. Gravity has already won. It has crushed atoms, destroyed nuclei, converted matter into a neutron sea, and it is still pulling, still squeezing, still trying to compress the star into a single point. The fact that it fails, the fact that the neutron star exists at all as a stable object and does not immediately become a black hole, is one of the most profound demonstrations of quantum mechanics in the entire universe. It tells us that quantum physics is not just a theory about tiny particles in laboratories. It is the force that holds dead stars together. It is the last wall between matter and oblivion. And right now, we are standing at the base of that wall, looking up, about to understand exactly what it is made of. To understand what holds a neutron star together, we need to leave behind everything classical physics taught us about pressure. We need to enter a realm where the rules are completely different, where pressure does not come from heat or motion in any familiar sense, where it comes instead from something woven into the deepest fabric of quantum mechanics, a principle so fundamental that it shapes the structure of atoms, the behavior of metals, the chemistry of life, and ultimately, the survival of dead stars. This principle is called the Pauli exclusion principle, and it is one of the most important ideas in all of physics. To get there, let's start with a question that seems completely unrelated to neutron stars. Why does the periodic table exist? Why do chemical elements have different properties? Why is helium inert while lithium is reactive? Why does carbon form the backbone of organic chemistry, while neon does absolutely nothing? The answer to all of these questions comes down to one thing. Electrons in atoms obey the Pauli exclusion principle. In the early 1920s, physics was in crisis. Scientists had figured out that atoms contain a nucleus surrounded by electrons. They knew that electrons occupy specific energy levels. Niels Bohr had proposed his famous model showing electrons orbiting the nucleus at fixed distances, each distance corresponding to a specific energy. The model worked beautifully for hydrogen, the simplest atom with just one proton and one electron. But for larger atoms with many electrons, things got confusing. If electrons could occupy any energy level, why didn't they all just fall to the lowest one? Why didn't every electron in every atom settle into the ground state, the lowest possible energy, hugging the nucleus as closely as quantum mechanics allowed? If that happened, all atoms would behave the same way. Chemistry would not exist. Carbon would be identical to oxygen, which would be identical to iron. There would be no periodic table, no chemical reactions, no molecules, no life. The diversity of the material world depends entirely on the fact that electrons do not all crowd into the lowest energy state. Something prevents them. Something forces them to spread out across higher and higher energy levels, giving each element its unique arrangement and its unique properties. In 1925, a young Austrian physicist named Wolfgang Pauli figured out what that something is. He proposed a rule that was deceptively simple, but had consequences reaching across all of physics. The rule states that no two identical fermions can occupy the same quantum state simultaneously. That is the Pauli exclusion principle. Let me unpack that because every word matters. First, fermions. Particles in the universe come in two broad families, fermions and bosons. The difference between them is a property called spin. Spin is not exactly the same as a ball spinning on its axis, but it is a quantum mechanical property that has some mathematical similarities. Fermions have half-integer spin. Their spin values are 1/2, 3/2, 5/2, and so on. Bosons have integer spin, 0, 1, 2. Electrons are fermions with spin 1/2. Protons are fermions with spin 1/2. Neutrons are fermions with spin 1/2. These are the particles that make up matter. Photons are bosons with spin 1. Gluons are bosons. The Higgs particle is a boson with spin 0. These are the particles that carry forces or give other particles mass. The distinction matters enormously because fermions and bosons follow completely different rules. Bosons are sociable. They love to pile into the same quantum state. In fact, the more bosons occupy a state, the more likely other bosons are to join. This is why lasers work. Photons are bosons, and when you stimulate emission in a laser, you get billions of photons, all in exactly the same quantum state. Same energy, same direction, same phase. Bosons clump together. They are cooperative. Fermions are the opposite. They are fundamentally antisocial. The Pauli exclusion principle says that no two identical fermions can be in the same quantum state at the same time. Not ever. Not under any circumstances. Not if you apply more force. Not if you raise the temperature. Not if you wait long enough. The rule is absolute. Two electrons in the same atom cannot have the same set of quantum numbers. If one electron occupies a particular state, every other electron in that atom is permanently locked out of that state. It is taken. Move on. Find another. This is not a suggestion. It is not a tendency or a preference. It is a fundamental law of nature with no known exceptions. It has been tested in countless experiments across nearly a century of physics. It holds for electrons, for protons, for neutrons, for quarks, for every fermion ever discovered. And it has consequences that are almost impossible to overstate. In an atom, each energy level can hold only a limited number of electrons. The lowest level holds two, one with spin pointing up and one with spin pointing down. Those are different quantum states, so the exclusion principle allows both. But once two electrons fill that lowest level, the next electron has no choice. It must go to the next level up, and the next two after that must go higher still. Electrons stack upward through the energy levels, not because they want to, not because some force pushes them there, but because the lower levels are already occupied, and the exclusion principle forbids doubling up. This is why atoms have structure. This is why elements differ from one another. This is why chemistry exists. Hydrogen has one electron in the lowest level. Helium has two, filling that level completely. Lithium has three, so the third electron must occupy a higher level, giving lithium completely different chemical properties from helium. Carbon has 6 electrons, arranged in a pattern that allows it to form 4 chemical bonds, making it the backbone of organic chemistry. Every element in the periodic table gets its unique identity from the specific arrangement of electrons forced into successive energy levels by the Pauli exclusion principle. Now, here is where this connects to stars. Consider what happens when you compress matter. When you squeeze atoms closer together, the electrons feel confined. They have less space to occupy. Quantum mechanics tells us that confining a particle to a smaller space increases its momentum. This is a direct consequence of the Heisenberg uncertainty principle. If you know a particle's position more precisely, meaning it is confined to a smaller region, its momentum becomes more uncertain, meaning it must be moving faster on average. Squeezing particles into tighter spaces forces them to move faster. Let me give you a way to picture this that makes physical sense. Imagine you have a marble rolling around inside a large box. The marble bounces off the walls occasionally, but since the box is large, the marble can drift slowly, bouncing gently, taking its time. Now shrink the box. Make it half the size. The marble still bounces off the walls, but now the walls are closer together. The marble hits a wall, reflects, and almost immediately hits the opposite wall. It has to move faster because there is less room to drift. Shrink the box again, and the marble moves faster still. It is ricocheting off the walls in rapid succession because there is almost no space left to move slowly. The smaller the box, the faster the marble must move. This is roughly what happens to quantum particles when you confine them. The mathematics is more subtle, involving wave functions and probability amplitudes rather than literal bouncing. But the physical intuition is sound. A particle in a smaller space has a shorter wavelength. A shorter wavelength means higher momentum. Higher momentum means faster motion. The universe will not allow a particle to sit still in a tiny space. The Heisenberg uncertainty principle demands motion, and the tighter the confinement, the more violent that motion becomes. For bosons, this is manageable. They can all crowd into the same lowest energy state even as the space shrinks. They cooperate. But for fermions, the exclusion principle changes everything. As you compress fermions into a smaller volume, the lowest energy states fill up quickly. Each fermion needs its own unique quantum state. As lower states are taken, new fermions are forced into higher and higher energy states, meaning they move faster and faster. They have no choice. The lower states are occupied. The exclusion principle forbids them from slowing down and joining the particles already in those states. This creates pressure. Real, physical, measurable pressure. Even if the temperature were absolute zero, meaning there is no thermal energy at all, the fermions would still be moving. They would still be exerting force on whatever confines them. Not because they are hot, but because quantum mechanics requires them to occupy distinct states, and in a confined space, that means occupying high-energy, high-momentum states. This pressure is called degeneracy pressure, and it is fundamentally different from any pressure you have encountered in everyday life. Let me say that again, because it is the most important point in this entire story. Degeneracy pressure does not come from heat. It does not come from thermal motion. It does not come from particles bouncing around randomly due to temperature. It exists even at zero temperature. It comes purely from the quantum mechanical requirement that identical fermions cannot share the same state. It is a pressure born from identity, from the fundamental nature of what fermions are. Think about how strange this is. In every other context you have encountered, pressure comes from energy. You heat a gas, the molecules move faster, and pressure increases. You cool a gas, the molecules slow down, and pressure drops. At absolute zero, classical physics says all motion stops. No motion means no pressure. But degeneracy pressure defies this logic entirely. You could cool a degenerate gas to absolute zero, drain every last joule of thermal energy from it, and the pressure would remain unchanged. The particles would still be moving. They would still be fast. Not because they have thermal energy, but because quantum mechanics forbids them from all settling into the lowest state. The exclusion principle forces motion even at zero temperature. It is pressure from identity, not from heat. Pressure from the fact that fermions are what they are. This is what holds up a white dwarf star. A white dwarf is the remnant left behind when a star like the Sun exhausts its nuclear fuel. The Sun is not massive enough to produce the extreme conditions that create a neutron star. Instead, when the Sun dies in about 5 billion years, it will shed its outer layers and leave behind a hot, dense core about the size of Earth, but with roughly half the mass of the Sun. That core is a white dwarf. Inside a white dwarf, there is no fusion. The nuclear furnace is dead. There is no thermal pressure strong enough to support the star against gravity. And yet, white dwarfs do not collapse. They sit there, stable, slowly cooling over billions and trillions of years. They can persist for longer than the current age of the universe. What holds them up is electron degeneracy pressure. The matter inside a white dwarf has been compressed to extraordinary densities, about 1 million times the density of water. At these densities, the electrons have been squeezed so tightly that their quantum states are nearly full. The lowest energy states are occupied. Electrons are being forced into higher and higher energy states because the Pauli exclusion principle forbids them from sharing. These high-energy electrons are moving very fast, at significant fractions of the speed of light, and their collective motion, driven not by heat but by quantum exclusion, generates an outward pressure that balances gravity. If you could somehow visit the interior of a white dwarf, you would find something unlike anything on Earth. The matter is so dense that a sugar cube-sized piece would weigh about a ton. The nuclei of atoms are packed into a rigid crystalline lattice, like the atoms in a diamond, but compressed to scales millions of times smaller. And threading through this lattice is a sea of electrons that have been stripped from their atoms and now move freely through the material, squeezed so tightly that quantum effects dominate their behavior completely. These electrons are not orbiting any particular nucleus. They belong to the star as a whole, and they are moving fast. Not because the white dwarf is hot, though young ones are, but because there is no room for them to move slowly. Every slow state is occupied. Only the fast states are available. The Pauli exclusion principle has forced them into a frenzied motion that holds the entire star up. This is elegant and profound. A dead star, cold and dark, with no energy source, is held up by a consequence of quantum identity. The electrons refuse to be in the same state. That refusal generates pressure, and that pressure is enough to hold off the gravitational collapse of a stellar core. But electron degeneracy pressure has a limit. In 1930, a young Indian physicist named Subramanian Chandrasekhar, only 19 years old at the time, calculated something remarkable during a sea voyage from India to England. He combined quantum mechanics with special relativity and worked out what happens to electron degeneracy pressure as you make a white dwarf more massive. He found that, as the white dwarf's mass increases, gravity compresses the star more. The electrons are squeezed harder. They move faster. As they approach the speed of light, something changes. In Newtonian mechanics, the faster a particle moves, the more pressure it exerts, and there is no limit to how fast it can go. But relativity says otherwise. Nothing can exceed the speed of light. As electrons approach light speed, they can no longer increase their speed in proportion to the squeeze. The pressure they generate grows more slowly. It starts to lose the race against gravity. Chandrasekhar calculated the exact mass at which electron degeneracy pressure can no longer hold gravity back. That mass is about 1.4 times the mass of the Sun. It is called the Chandrasekhar limit, and it is one of the most important numbers in astrophysics. Below this mass, a white dwarf is stable. Electron degeneracy pressure wins. Above this mass, electron degeneracy pressure fails. Gravity wins. The star collapses further. And this is exactly what happens in the formation of a neutron star. When a massive star's core collapses at the end of its life, the resulting remnant typically exceeds the Chandrasekhar limit. Electron degeneracy pressure tries to hold the core up, but it cannot. The mass is too great. Gravity overwhelms the electrons. Now, what happens to those electrons when gravity overpowers their degeneracy pressure is extraordinary. The compression becomes so intense that electrons are forced into direct contact with protons. The inverse beta decay process we already encountered takes over on a massive scale. Electrons are captured by protons, each pair merging into a neutron, while a neutrino carries energy away. This is not a gradual trickle. It is a wholesale transformation of the matter itself. Trillions upon trillions of electrons are devoured by protons during the core collapse. The matter transforms completely. What was once a mixture of electrons, protons, and neutrons inside atomic nuclei becomes an ocean of almost pure neutrons. The electrons that were generating degeneracy pressure, the very particles whose quantum stubbornness held up the white dwarf for billions of years, are consumed, absorbed, converted, gone. The particles that held up the previous star are removed from the equation entirely. It would seem like gravity has won completely. The electrons are gone. Their pressure is gone. There is nothing left to resist. The core should collapse all the way to a singularity, to a black hole, to a point of infinite density. But it does not, because neutrons are also fermions. This is the crucial insight. Neutrons, like electrons, have spin 1/2. They are fermions. They obey the Pauli exclusion principle just as strictly as electrons do. No two neutrons can occupy the same quantum state. And when trillions upon trillions of neutrons are compressed into a volume just 20 kilometers across, the same quantum mechanics that generated electron degeneracy pressure now generates neutron degeneracy pressure. The mechanism is identical in principle. As the neutrons are squeezed into a smaller and smaller volume, the lowest energy quantum states fill up. Each neutron needs its own unique state. New neutrons are forced into higher and higher energy levels. They move faster and faster. Their collective motion generates an outward pressure that has nothing to do with temperature. It is pure quantum mechanical exclusion. The neutrons refuse to share states. That refusal pushes back against gravity. But there is a critical difference between electron degeneracy pressure and neutron degeneracy pressure, and it explains why neutron stars can survive where white dwarfs cannot. Neutrons are about 1,839 times more massive than electrons. This matters enormously. Degeneracy pressure depends on the mass of the particle involved. Heavier particles generate stronger degeneracy pressure at the same density. This might seem counterintuitive. You might expect lighter particles, moving faster, to exert more pressure. And indeed, at the densities found inside white dwarfs, electron degeneracy pressure is sufficient. But at the far higher densities inside a collapsing stellar core, what matters is that heavier particles can be packed to much higher densities before their degeneracy pressure becomes relativistic and starts losing effectiveness. Think of it this way. Electron degeneracy pressure fails at the Chandrasekhar limit because the electrons approach the speed of light. They cannot move any faster, so they cannot generate any more pressure. But neutrons, being much more massive, move more slowly at the same momentum. At the densities where electron degeneracy pressure fails, neutron degeneracy pressure is just getting started. The neutrons are nowhere near the speed of light yet. They have plenty of room to be squeezed further before relativistic effects kick in. So neutron degeneracy pressure can resist gravitational forces far beyond what electrons could handle. It is as if gravity defeated the first line of defense and then immediately encountered a second, far stronger wall built from the same quantum principle but using much heavier building blocks. The exclusion principle did not disappear when the electrons were consumed. It simply transferred to the neutrons, and the neutrons fight harder. Let me make this tangible. Inside a white dwarf, the electron degeneracy pressure supports the star at densities of about 1,000,000 grams per cubic centimeter. That is impressive. 1 cubic centimeter of white dwarf material weighs about a ton. But inside a neutron star, the neutron degeneracy pressure supports the star at densities of about 200 trillion to 1 quadrillion grams per cubic centimeter. That is hundreds of millions of times denser than a white dwarf. The quantum wall built from neutrons is not just stronger, it is almost incomprehensibly stronger. And the extraordinary thing is that none of this depends on temperature. A neutron star could be at absolute zero, the coldest possible temperature, the complete absence of thermal energy, and the degeneracy pressure would be exactly the same. The neutrons would still be moving, they would still be fast, they would still exert tremendous pressure. Because the Pauli exclusion principle does not care about temperature, it cares about quantum states. As long as the neutrons are packed tightly enough that the available quantum states are nearly full, the pressure is there. It is automatic. It is built in. It is a property of the matter itself, not of any energy source driving it. This is fundamentally different from how a normal star works. The sun depends on fusion to generate heat, and heat generates pressure. If the sun's fusion stopped, it would collapse. A neutron star depends on the quantum nature of fermions to generate pressure. No energy source is needed. No reaction needs to be sustained. The pressure exists because the particles exist, and because quantum mechanics requires them to behave in a particular way. It is not fuel that can be burned up. It is not a process that can run down. It is a feature of the quantum world as permanent and reliable as the exclusion principle itself. This is why neutron stars can last essentially forever. They cool over time. They radiate away their thermal energy. Their surface temperatures drop from millions of degrees to thousands, then to hundreds. But the degeneracy pressure does not diminish. The star does not weaken as it cools. The quantum wall stands regardless of temperature. A neutron star a trillion years from now, cold and dark and ancient, will be just as structurally sound as the day it was born. The pressure holding it up will not have decreased by a single Pascal. There is something almost eerie about this. We are accustomed to things wearing out. Batteries die, engines fail, fires go cold. But degeneracy pressure is not a mechanism that can wear down. It is a constraint imposed by the laws of quantum physics. As long as the matter exists, and as long as the Pauli exclusion principle holds, the pressure is there. The only way to defeat it is to add enough mass that even the speed of light cannot help the neutrons. Just as the Chandrasekhar limit marked the point where electron degeneracy pressure could no longer keep up. There is a corresponding limit for neutron stars, and we will get to that. But the point for now is that the pressure itself is eternal. It does not decay. It does not require maintenance. It is built into the quantum fabric of reality. You might wonder whether this quantum pressure is really strong enough to matter at cosmic scales. After all, quantum mechanics is usually associated with tiny particles, with atoms and electrons and photons. How can a quantum effect hold up an entire star? The answer is that when you pack enough fermions into a small enough space, the quantum effects are not small at all. They dominate. At neutron star densities, the quantum pressure from neutron degeneracy is not a subtle correction to some other, larger force. It is the primary force. It is the main event. Gravity pulls inward with a force generated by 1.5 solar masses compressed into a 20-kilometer sphere, and neutron degeneracy pushes outward with enough strength to balance that pull. These are not small numbers. The pressures involved are trillions of times greater than anything found inside ordinary stars. And the source of that pressure is quantum exclusion. The Pauli exclusion principle, a rule discovered by a 25-year-old physicist trying to explain why electron shells in atoms have limited capacity, turns out to be the force that prevents dead stars from collapsing into black holes. A rule about quantum identity, about the nature of fermions, about the mathematical properties of particle wave functions, becomes the last line of defense against the most extreme gravitational environments in the universe outside of black holes themselves. This is one of the most beautiful connections in all of science. The same principle that gives the periodic table its structure, that makes chemistry possible, that allows atoms to have different sizes and different properties, that ultimately makes complex matter and life possible. That same principle holds up neutron stars. The physics of the very small governs the fate of the very large. The quantum world reaches up and shapes the cosmos. But neutron degeneracy pressure is not the entire story. It is the dominant player, but inside a neutron star, the conditions are so extreme that other forces enter the picture. The strong nuclear force, the force that binds protons and neutrons together inside atomic nuclei, behaves in strange and powerful ways at neutron star densities. And at the very center of the star, where densities reach 5 to 10 times the density of an atomic nucleus, the matter may enter phases so exotic that our current physics cannot fully describe them. Neutron degeneracy pressure built the wall, but the wall has layers, and what lies behind those layers is where the story gets even stranger. We have established that neutron degeneracy pressure is the primary force resisting gravitational collapse inside a neutron star. The Pauli exclusion principle forbids neutrons from sharing quantum states, and that refusal generates a tremendous outward pressure that owes nothing to heat. But if you think that is the complete answer, that neutron degeneracy pressure alone explains everything happening inside these extraordinary objects, the reality is far more complicated and far more fascinating. A neutron star is not a uniform ball of identical neutrons all pressing against each other in the same way from surface to center. It is a layered structure, almost like a planet in that sense, with distinct regions where the physics changes dramatically as you move inward. And in the deepest layers, where densities climb to values 5 to 10 times greater than the density of an atomic nucleus, forces beyond simple degeneracy enter the picture. Forces that arise from the strong nuclear interaction, the most powerful force in the known universe. Forces that may push matter into exotic states that have never been observed in any laboratory on Earth. To understand this, we need to talk about the strong nuclear force and how it behaves under extreme compression, because this force does something remarkable. At very short distances, it becomes fiercely repulsive, and that repulsion contributes a second major source of pressure inside a neutron star, layered on top of the degeneracy pressure we have already discussed. The strong nuclear force is the force that holds atomic nuclei together. Protons are positively charged. They repel each other electromagnetically. Two protons sitting next to each other should fly apart because like charges repel. And yet, inside every atomic nucleus heavier than hydrogen, protons sit side by side, packed together with neutrons, forming stable structures that can last for billions of years. Something must be overpowering the electromagnetic repulsion. That something is the strong force. At the scale of an atomic nucleus, roughly 1 femtometer, which is 1 quadrillionth of a meter, the strong force is about 100 times more powerful than electromagnetism. It overwhelms the electrical repulsion between protons and binds nucleons, both protons and neutrons, into tight nuclear packages. Without it, no element heavier than hydrogen would exist. There would be no carbon, no oxygen, no iron, no planets, no life. The strong force is what makes complex matter possible. But the strong force has a peculiar character. It is not simply attractive, its behavior changes depending on the distance between particles. At moderate nuclear distances, around 1 to 2 femtometers, the strong force is powerfully attractive. This is the regime where it binds nuclei together. It pulls nucleons toward each other, holding them in place against the electromagnetic repulsion of the protons. This attractive behavior is what gives nuclei their stability. However, at very short distances, below about half a femtometer, the strong force changes character. It switches from attractive to intensely repulsive. Nucleons that are pushed too close together experience a hardcore repulsion, a wall of force that resists further compression. This is sometimes described as the hard core of the nuclear force. It means that nucleons behave somewhat like hard spheres. You can push them close together, and the attractive part of the strong force will happily pull them into contact. But try to push them closer still, try to overlap them, try to force them into the same space, and the repulsive core pushes back with extraordinary strength. This is not degeneracy pressure. This is a completely different physical mechanism. Degeneracy pressure comes from quantum statistics, from the exclusion principle's requirement that fermions occupy distinct quantum states. The strong force repulsion comes from the actual interaction between particles, from the way the strong force field behaves at very short range. These are two separate sources of pressure operating simultaneously inside a neutron star. Think of it this way. Imagine a room full of people. The Pauli exclusion principle is like a rule that says no two people can stand in exactly the same spot. Even if they wanted to, even if someone pushed them, they cannot occupy the same location. That rule creates a kind of pressure as the room fills up. People are forced to spread out to fill every available space, simply because overlapping is forbidden. That is degeneracy pressure. Now add a second effect. Each person is also wearing a suit of armor that extends a certain distance from their body. When two people in armor get too close, the armor physically pushes them apart. This has nothing to do with the rule about not occupying the same spot. It is a separate mechanical force. The armor creates its own repulsion. That is the strong force repulsion. Inside a neutron star, both effects operate together. The neutrons cannot share quantum states, so they resist compression through degeneracy. And simultaneously, the strong nuclear force between neighboring neutrons resists them being pushed closer than about half a femtometer through its repulsive core. The total pressure holding the star up is a combination of both. Neither alone tells the full story. At the densities found in the outer parts of a neutron star, degeneracy pressure dominates. The neutrons are close, but not extremely close. The strong force is mostly attractive at these separations, pulling neighboring neutrons toward each other gently. The degeneracy pressure from quantum exclusion does most of the work against gravity. But deeper inside the star, where densities climb to several times nuclear saturation density, the neutrons are squeezed so tightly that they begin to feel the repulsive core of the strong force. Now both mechanisms contribute significantly. The strong force repulsion adds a stiffness to the matter that pure degeneracy pressure alone would not provide. It makes the material harder to compress, stiffer, more resistant to the inward pull of gravity. This additional stiffness is crucial because at these extreme densities, degeneracy pressure alone might not be enough. The combination of quantum exclusion and nuclear repulsion together creates a pressure that can withstand gravitational forces far greater than either source could resist on its own. Now let's walk through the actual structure of a neutron star from the outside in. Because the interior is not uniform, it is layered, and each layer contains matter in a different state, subject to different physics. The outermost layer is the atmosphere. It is incredibly thin, perhaps only a few centimeters to a few meters deep. It contains ordinary atoms, mostly hydrogen and helium, along with some heavier elements. The temperatures here can be hundreds of thousands to millions of degrees on a young neutron star. This is the layer that emits the radiation we actually detect with telescopes. The atmosphere is conventional matter, obeying conventional physics. It is the only part of a neutron star where you would recognize the material as something familiar. Below the atmosphere is the outer crust. This layer extends down perhaps 1 to 2 kilometers. Here, the matter is compressed far beyond anything found on Earth, but it still contains recognizable atomic nuclei. The nuclei are squeezed into a crystalline lattice, a rigid structure where nuclei sit at fixed points, surrounded by a sea of electrons. Think of it as an incredibly dense metal. The nuclei are iron and heavier elements, the products of nuclear fusion in the star's previous life, compressed to densities of millions to billions of grams per cubic centimeter. The electrons are degenerate, meaning their degeneracy pressure contributes to the structure. The outer crust behaves somewhat like an extremely exotic solid, rigid and crystalline, held together by electromagnetic forces between the nuclei and the electron sea. As you go deeper into the crust, the pressure increases, and something interesting happens to the nuclei. They become increasingly neutron-rich. Under extreme pressure, it becomes energetically favorable for the nuclei to absorb electrons, converting protons into neutrons through inverse beta decay. The nuclei that exist in the outer crust are not the same nuclei you find in a laboratory. They are exotic, heavily neutron-rich isotopes that would be wildly unstable under normal conditions, but are stabilized here by the immense pressure. At a density of roughly 400 billion grams per cubic centimeter, you cross a critical threshold called the neutron drip line. This is where the inner crust begins. Below this line, the nuclei are so stuffed with neutrons that they can no longer hold them all. Neutrons begin to leak out, dripping free from the nuclei like water overflowing from an overfull cup. The inner crust is a strange environment. It contains neutron-rich nuclei sitting in a lattice, just like the outer crust. But now those nuclei are immersed in a fluid of free neutrons that have dripped out. There are also degenerate electrons present. It is a 3-component system. solid nuclei, free neutron fluid, and an electron gas. Nothing like this exists anywhere else in the known universe. The inner crust extends down another kilometer or so. As you go deeper, the density keeps rising, and the nuclei become increasingly swollen with neutrons. The free neutron fluid becomes denser, and something truly bizarre begins to happen to the shapes of the nuclei themselves. Under normal conditions, atomic nuclei are roughly spherical. The strong force and electromagnetic force conspire to keep them round. But at the extreme pressures near the bottom of the inner crust, the competition between nuclear attraction and electromagnetic repulsion among the protons distorts the nuclei into exotic shapes. They elongate into rods, flatten into slabs, develop holes and tunnels. Physicists have given these shapes whimsical names borrowed from Italian food. Spherical nuclei become elongated into spaghetti-like rods. The rods merge into flat, lasagna-like sheets. The sheets develop cylindrical holes called anti-spaghetti. The holes merge into spherical voids called Swiss cheese, and tiny disconnected blobs are sometimes called gnocchi. These phases are collectively known as nuclear pasta. Nuclear pasta is not a joke. It is a serious prediction of nuclear physics supported by extensive computer simulations. The shapes arise because the matter is at a transition point between distinct nuclear clusters and a uniform nuclear fluid. The competition between the attractive strong force, which tries to pull nucleons together, and the repulsive electromagnetic force between protons, which tries to push them apart, creates frustration. Neither force can completely dominate. The result is these exotic intermediate shapes, structures that maximize the attractive nuclear force while minimizing the electromagnetic repulsion. Nuclear pasta may be the strongest material in the universe. Simulations suggest that the spaghetti and lasagna phases can withstand enormous stresses before breaking. The material is estimated to be roughly 10 billion times stronger than steel. If this is correct, the inner crust of a neutron star contains a layer of material more durable than anything else that exists anywhere. Below the inner crust, at densities exceeding roughly 200 trillion grams per cubic centimeter, you enter the outer core. This is where the nuclei finally dissolve completely. The last remnants of nuclear structure vanish. There are no more lattices, no more pasta shapes, no more identifiable nuclei of any kind. What remains is a uniform fluid of neutrons with a small admixture of protons and electrons, and possibly muons, which are heavier cousins of electrons. This neutron fluid makes up the bulk of the neutron star's volume and mass. The outer core extends from the base of the crust down to roughly the central few kilometers of the star. Here, the density ranges from about nuclear saturation density, roughly 230 trillion grams per cubic centimeter, up to about 2 to 3 times that value. In this regime, the physics is reasonably well understood, at least compared to what comes deeper. The matter is a degenerate neutron fluid with strong force interactions between the particles. Both neutron degeneracy pressure and the repulsive core of the strong nuclear force contribute significantly to the pressure. The neutron fluid in the outer core is predicted to be a superfluid, and this is one of the strangest predictions in all of neutron star physics. So let me take a moment to explain just how bizarre it is. Superfluidity is a quantum state of matter in which a fluid flows without any viscosity, without any friction, without losing energy to resistance. It sounds almost magical. A superfluid can flow through incredibly narrow channels without slowing down. It can climb the walls of its container. It exhibits bizarre quantum behavior on a macroscopic scale. On Earth, superfluidity has been observed in liquid helium cooled to within a few degrees of absolute zero. That is about minus 456 degrees Fahrenheit. At those temperatures, helium atoms slow down so much that their quantum wave functions overlap, and the entire fluid begins acting as a single, coherent quantum object. That is the only way we have ever produced superfluidity in a laboratory. By cooling matter to within a hair's breadth of absolute zero. Inside a neutron star, the temperature is not remotely close to absolute zero. A young neutron star can have an internal temperature of tens of billions of degrees in the moments after its birth. Even an old one has a core temperature of millions of degrees. By any normal standard, this is ferociously hot. Superfluidity at these temperatures should be absolutely impossible. In every laboratory experiment ever conducted, superfluidity requires extreme cold. Heat destroys it. Thermal energy disrupts the delicate quantum coherence that makes superfluidity work. And yet, the neutrons in a neutron star's outer core are predicted to form a superfluid anyway. The reason is density. At the unimaginable densities inside a neutron star, the quantum effects are so overwhelmingly strong that they dominate even at temperatures that would instantly destroy superfluidity in any terrestrial material. The neutrons pair up, forming what are called Cooper pairs, named after the physicist Leon Cooper, who first described the pairing mechanism in superconductors. These paired neutrons behave as bosons because two fermions paired together produce a composite particle with integer spin. And bosons, as we discussed earlier, love to crowd into the same quantum state. The paired neutrons condense into a single coherent quantum state, a superfluid, even in the blistering heat of a neutron star's interior. This means that deep inside a neutron star, there is an ocean of neutron fluid spanning several kilometers in every direction, flowing with zero viscosity. If you could somehow stir this fluid, it would never stop swirling. There is no friction to slow it down, no resistance to dissipate its motion. The rotation would persist forever, unchanged, because a superfluid does not experience drag. It cannot be slowed by ordinary means. We actually have observational evidence that this happens. Pulsars, the rapidly spinning neutron stars that sweep beams of radiation across space like cosmic lighthouses, occasionally exhibit sudden tiny speed-ups in their rotation, called glitches. The star is spinning at a steady rate, hundreds of times per second in some cases, and then, suddenly, in less than a minute, the rotation rate jumps by a tiny but measurable amount. The leading explanation for these glitches involves the superfluid interior. The superfluid component of the star, rotating independently of the solid crust, stores angular momentum in quantized vortices. When the crust slows down slightly due to electromagnetic braking, the superfluid does not slow down with it, because superfluids do not experience friction. A tension builds between the crust and the superfluid. Eventually, vortices in the superfluid unpin from the crust, releasing stored angular momentum in a sudden burst. The crust speeds up. A glitch. The Velar pulsar has exhibited many such glitches over the decades, and they provide some of the best indirect evidence that neutron star interiors contain superfluid neutrons. Similarly, the small population of protons in the outer core may form a superconductor. A superconductor is a material that conducts electrical current with zero resistance. In a superconducting state, the protons would carry currents that never dissipate, never lose energy, never decay. These persistent currents could sustain the powerful magnetic fields observed on neutron stars for millions or billions of years without any external power source. The magnetic fields of neutron stars can be 1 trillion times stronger than Earth's magnetic field, and, in extreme cases, called magnetars, they can be 1,000 times stronger still. These are the most powerful magnetic fields known to exist in the universe, and they may persist for geological timescales because the proton superconductor that sustains them has literally zero electrical resistance. Think about what this means in practical terms. On Earth, if you run an electrical current through a wire, That current gradually diminishes because the wire has resistance. The energy dissipates as heat. To maintain the current, you need to keep supplying energy. A battery, a power plant, something. But in a superconductor, the current flows forever with no energy input. It does not diminish. It does not heat the wire. It does not need a battery. It just flows indefinitely. Now imagine that phenomenon operating not in a laboratory sample cooled to near absolute zero, but inside a star, at temperatures of millions of degrees, sustaining magnetic fields strong enough to rip the electrons from atoms at a distance of 1,000 kilometers. That is what may be happening inside the outer core of a neutron star right now. These are exotic states of matter on a scale that dwarfs anything achievable in a laboratory. We can create tiny samples of superfluid helium in cryogenic experiments. We can make superconducting materials that work at temperatures far below room temperature. But a neutron star contains a superfluid ocean of neutrons spanning kilometers, at densities exceeding that of atomic nuclei, sustaining superconducting currents that generate magnetic fields 1 trillion times stronger than Earth's magnetic field. The quantum mechanics that we test in tabletop experiments with milligram samples is operating here on a stellar scale. And then we reach the inner core. This is where the deepest mysteries lie. The inner core occupies the central few kilometers of the neutron star, and the density there may reach 5 to 10 times nuclear saturation density. These are densities that have never been produced in any laboratory on Earth. No particle accelerator, no nuclear experiment has created sustained bulk matter at these densities. We do not know what happens to matter under these conditions. We are at the frontier of human knowledge. There are several possibilities, and physicists have been debating them for decades. The first possibility is that the matter remains composed of neutrons, protons, and electrons, just as in the outer core, but interacting through the strong force in ways that become increasingly difficult to calculate. At these densities, the particles are so close together that the repulsive core of the strong force dominates. The matter is incredibly stiff, resisting compression powerfully. The pressure is enormous. This is the simplest scenario, but even this simple picture is hard to calculate because the strong force at short range is notoriously difficult to model mathematically. The second possibility is that new particles appear. At sufficiently high densities, it may become energetically favorable for some neutrons to transform into heavier particles called hyperons. Hyperons are baryons, particles in the same family as protons and neutrons, but they contain one or more strange quarks. A neutron is made of 2 down quarks and 1 up quark. A lambda hyperon replaces one of those down quarks with a strange quark. A sigma hyperon is another variant. Under normal conditions, hyperons are unstable. They decay in a tiny fraction of a second. But at the extreme densities inside a neutron star's inner core, the energy required to maintain them may be less than the energy required to keep all the matter as neutrons. The Pauli exclusion principle plays a role here too. If the neutron energy levels are all filled up to very high values, it may cost less energy to create a hyperon in a lower energy state than to add another neutron to an already packed neutron population. But hyperons create a problem. When they appear, they tend to soften the equation of state. They reduce the pressure at a given density because they open up new quantum states that particles can occupy, relieving some of the degeneracy pressure. Less pressure means less support against gravity. Less support means the maximum mass a neutron star can reach before collapsing decreases. Some calculations, including hyperons, predict maximum neutron star masses well below what has actually been observed. We have measured neutron stars with masses around 2 solar masses, and some hyperon models cannot produce neutron stars that heavy. This discrepancy is called the hyperon puzzle, and it remains one of the major unsolved problems in neutron star physics. The third possibility is even more exotic. At the highest densities, the individual neutrons and protons themselves may dissolve. Remember, Neutrons and protons are not fundamental particles. They are made of quarks held together by gluons, the carriers of the strong force. Under normal conditions, quarks are permanently confined inside their parent particles. You cannot isolate a single quark. The strong force between quarks actually gets stronger as you try to pull them apart, which is the opposite of how gravity and electromagnetism behave. Pulling quarks apart is like stretching a rubber band. The farther you stretch, the harder it pulls back. Eventually, if you pump enough energy in, the rubber band snaps, but instead of freeing a quark, the energy creates a new quark-antiquark pair. You end up with more particles, but still no free quarks. However, at extreme densities, theory predicts that something different can happen. When nucleons are squeezed so tightly that they overlap, the quarks inside them may no longer belong to any particular nucleon. They become free to roam throughout the dense medium. This is called quark deconfinement, and the resulting state of matter is called quark matter, or more precisely, cold, dense quark matter. If quark matter exists in the cores of neutron stars, it would be fundamentally different from anything on the surface. The individual neutrons would have dissolved into a soup of up quarks, down quarks, and strange quarks, swimming in a sea of gluons. The pressure in this phase would come from a completely different source: quark degeneracy pressure, because quarks are also fermions with spin 1/2. They obey the Pauli exclusion principle just as electrons and neutrons do. And the interactions between quarks at these densities, mediated by the strong force in its fundamental form, described by the theory called quantum chromodynamics, or QCD, would contribute additional pressure. Some theorists have proposed that this quark matter might be in a special state called color superconductivity, where quarks form pairs analogous to the Cooper pairs that produce superconductivity in metals. Color superconducting quark matter would have remarkable properties. It would be extremely stiff, resisting compression even more effectively than ordinary neutron matter. This could actually help solve the hyperon puzzle, because if the core transitions to quark matter before hyperons become important, the softening effect of hyperons might be avoided. There is an even more speculative possibility. In 1984, physicist Edward Witten proposed that strange quark matter, a mixture of up, down, and strange quarks in roughly equal proportions, might actually be the true ground state of matter. If this is correct, then ordinary nuclear matter, the protons and neutrons that make up everything around us, is merely metastable. Given enough time or the right conditions, it would convert to strange matter, which has lower energy. A neutron star's core might provide exactly those conditions. If strange matter is the true ground state, then the entire core of a sufficiently massive neutron star might convert to a strange quark star, an object made almost entirely of deconfined quarks in the strange matter phase. This is speculative. We do not have experimental confirmation that strange matter is stable, but it is a theoretically consistent possibility that remains actively investigated. If strange stars exist, they would look very similar to neutron stars from the outside. They would have similar masses and radii. The difference would be in their internal composition and in subtle details of their behavior. The point of all these possibilities is that we genuinely do not know what the inside of a neutron star looks like at its deepest level. We know the outer layers reasonably well. We understand the crust, the neutron drip regime, even the nuclear pasta phases with fair confidence. We understand the outer core, where the physics of dense neutron matter is constrained by nuclear experiments and theory. But the inner core remains mysterious. The relationship between density and pressure inside a neutron star is described by something called the equation of state. This is a mathematical function that tells you, for any given density, how much pressure the matter produces. The equation of state is the single most important piece of information for understanding neutron stars. If you know the equation of state, you can calculate the maximum mass a neutron star can have, its radius, how it deforms under tidal forces, how it vibrates when disturbed, and how it ultimately collapses if pushed beyond its limits. But we do not know the equation of state at densities above about 2 times nuclear saturation density. Not precisely. We have models, we have theoretical frameworks, we have computer simulations, but we do not have certainty. The strong force at these densities is extraordinarily difficult to calculate. The mathematical tools that work beautifully for electromagnetism and even for the strong force at lower energies become unreliable at the extreme conditions found in neutron star cores. Lattice QCD, the most rigorous method for calculating strong force behavior from first principles, faces severe technical obstacles at high densities. Perturbative QCD, which works at very high energies where the strong force becomes weak, is not applicable at neutron star densities where the force is still strong. We are in a regime where the force is too strong for simple approximations, but too complicated for exact solutions. This means that the equation of state at neutron star core densities is one of the biggest unsolved problems in nuclear and particle physics. It is not a niche question. It connects to fundamental questions about the nature of matter under extreme conditions. It connects to the behavior of the strong force, one of the four fundamental forces of nature. It connects to whether quarks can exist freely outside of hadrons. It connects to whether strange matter is the true ground state. These are deep, foundational questions about how the universe works at its most basic level. And the pressure inside a neutron star is the physical manifestation of the answers. Whatever the equation of state turns out to be, it will be written in pressure. Pressure as a function of density. That function encodes everything about the strong force at extreme densities, about the composition of ultra-dense matter, about whether hyperons appear, whether quarks deconfine, whether strange matter is stable. All of it is encoded in one curve, one relationship. Density in, pressure out. The neutron star does not care about our theoretical uncertainties. It exists. It is stable. The pressure inside it, whatever its precise source, is sufficient to hold gravity at bay. And that pressure comes from a combination of effects. Neutron degeneracy pressure from the Pauli exclusion principle, repulsive strong force interactions at short range, possible contributions from hyperons, from quark matter, from exotic phases we have not yet imagined. The star is a laboratory, and its structure is the experiment. Our job is to figure out how to read the results. The interior of a neutron star is one of the most extreme environments in the universe. It is denser than an atomic nucleus. It may contain phases of matter found nowhere else in the cosmos. Its pressure arises from the deepest principles of quantum mechanics and the strongest force in nature, operating together under conditions that push both to their limits. And despite decades of research by thousands of physicists, we still do not fully understand what is happening in the innermost few kilometers. What we do know is that the pressure is there. Multiple sources contribute. The quantum exclusion of neutrons, the repulsive core of the strong nuclear interaction, and possibly the degeneracy of deconfined quarks, all push outward against gravity. The star is held up not by one simple mechanism, but by a combination of quantum and nuclear effects, layered and intertwined, each dominating in different regions and at different densities. It is a symphony of forces, not a single note. And like any symphony, it has a finale. There is a point beyond which even this extraordinary combination of pressures cannot hold. There is a maximum mass, a breaking point, a threshold beyond which the neutron star loses its battle and gravity finishes what it started. That limit and what it means is where we go next. Everything we have discussed so far has been about survival, about how quantum mechanics and the strong nuclear force conspire to generate enough pressure to hold a dead star together against gravitational forces that have already destroyed atoms, erased chemistry, and compressed matter beyond nuclear density. But every defense has a limit. Every wall can be breached if you push hard enough, and the wall inside a neutron star, as extraordinary as it is no exception. There is a maximum mass that a neutron star can have. Beyond that mass, no combination of degeneracy pressure, strong force repulsion, or exotic matter can generate enough outward push to resist gravity. The star collapses. Not into a denser star, not into some new stable object. It collapses completely, forming a black hole. A region of space-time where gravity has won so thoroughly that nothing, not matter, not light, not information, can ever escape. This maximum mass is called the Tolman-Oppenheimer-Volkoff limit, named after the three physicists who worked out the mathematics. Richard Tolman, J. Robert Oppenheimer, and George Volkoff published their analysis in 1939, the same year World War II began. Using Einstein's equations of general relativity, they calculated the structure of a star made of cold, dense, degenerate matter, and asked a simple question. How massive can such a star be before gravity overwhelms the internal pressure? Their calculation was remarkable for its time. General relativity was barely 2 decades old. Quantum mechanics was even younger. And yet, Oppenheimer and Volkoff combined both frameworks to derive the conditions under which a neutron star can exist in stable equilibrium. They found that there is a critical mass above which no stable solution exists. Add more matter than this limit allows, and the equations have no answer that corresponds to a stable, non-collapsing star. The only outcome is continued collapse, forever, into a singularity. The exact value of this limit depends on the equation of state, the relationship between pressure and density inside the star. And as we discussed, we do not know the equation of state precisely at the extreme densities found in neutron star cores. Different models give different maximum masses, but the observational evidence and theoretical constraints together point to a limit somewhere between about 2 and 2.5 solar masses. Some models place it a bit lower, some a bit higher, but the range is well established. A neutron star cannot exceed roughly 2.5 times the mass of the Sun without collapsing into a black hole. Most estimates center around 2.2 to 2.3 solar masses as the probable upper bound. To understand why this limit exists, let's return to the analogy with white dwarfs. The Chandrasekhar limit, about 1.4 solar masses, is the maximum mass for a white dwarf supported by electron degeneracy pressure. That limit exists because as the white dwarf gets more massive, gravity compresses it harder, the electrons move faster to maintain degeneracy pressure, and eventually, the electrons approach the speed of light. Once they become relativistic, their pressure can no longer increase fast enough to keep up with gravity. The star collapses. The same basic logic applies to neutron stars, but at a much higher mass scale. As a neutron star gets more massive, gravity compresses it harder. The neutrons are forced into higher energy states. They move faster. The strong force repulsion between neutrons stiffens the matter. But there are limits. As the density increases, even these combined pressures start to lose ground against gravity. And general relativity makes things worse. Here is something that most people do not realize about gravity at these extremes. In Newtonian gravity, the gravity of an object depends on its mass and the distance from its center. Mass creates gravity. That is straightforward. But in general relativity, Einstein's far more accurate theory of gravity, pressure also creates gravity. This sounds paradoxical. Pressure is what holds the star up. How can it also contribute to the force pulling the star down? In general relativity, the source of gravity is not just mass. It is energy and momentum in all their forms. Mass is a form of energy, as Einstein showed with E equals mc squared. But pressure is also a form of energy density. At the extreme conditions inside a neutron star, the pressure is so enormous that it contributes significantly to the gravitational field. The very pressure that resists collapse also adds to the gravitational pull trying to cause collapse. The harder the matter pushes outward, the more gravity it creates, which requires even more pressure to resist, which creates even more gravity. Let me try to make this tangible with an analogy, because this idea is genuinely counterintuitive. Imagine you are standing in quicksand. You are sinking, so you push down with your arms to lift yourself up. But the act of pushing down drives you slightly deeper, which means you have to push even harder, which drives you deeper still. Your effort to escape contributes to the force trapping you. The harder you fight, the harder it becomes to fight. In Newtonian gravity, pushing yourself up would simply work. You push, you rise, problem solved. But general relativity adds this cruel twist. In the most extreme gravitational environments, the act of pushing back against gravity literally adds to the gravitational field you are pushing against. Inside a neutron star near the Tolman-Oppenheimer-Volkoff limit, this effect becomes devastating. The matter is pushing outward with unimaginable pressure, trillions upon trillions of pascals of degeneracy pressure and strong force repulsion shoving against gravity. But every pascal of that pressure adds to the effective gravitational mass of the star. The pressure is fighting gravity, but it is also feeding gravity. At moderate densities, this effect is small. Pressure contributes only a little to the gravitational field. The star barely notices. But at the extreme densities near the core of a maximally massive neutron star, the pressure is so enormous that its contribution to gravity becomes significant. The star is caught in a tightening loop. More compression creates more pressure, but more pressure creates more gravity, which demands even more pressure, which creates even more gravity. This is a feedback loop, and it is ultimately what destroys the neutron star's ability to hold itself up beyond a certain mass. In Newtonian gravity, you could in principle always add more pressure to resist more gravity. The two forces are independent. But in general relativity, they are coupled. Pressure fights gravity, but pressure also feeds gravity. At some point, the feedback becomes uncontrollable. Adding more pressure generates more gravity than the pressure can support. The situation becomes unstable. No amount of pressure, no matter how exotic, no matter how stiff the equation of state, can prevent collapse beyond this point. This is a deep and almost tragic feature of general relativity. The universe has built into it a fundamental limit on how much pressure can help. Beyond the Tolman-Oppenheimer-Volkoff limit, the star is doomed. Not because the matter is weak, not because quantum mechanics fails, not because the strong force gives out, but because the very act of resisting gravity creates more gravity to resist. The defense contributes to the attack. The wall strengthens the force trying to tear it down. It is one of the most profoundly counterintuitive results in all of physics, and it comes directly from the geometry of space-time as Einstein described it. Let me put this in perspective by comparing the two limits side by side. The Chandrasekhar limit for white dwarfs is about 1.4 solar masses. The Tolman-Oppenheimer-Volkoff limit for neutron stars is roughly 2 to 2.5 solar masses. The gap between them is only about 1 solar mass. That narrow range is all the room the universe allows for neutron stars to exist. Below 1.4 solar masses, an object can survive as a white dwarf, supported by electron degeneracy pressure. Between roughly 1.4 and about 2 to 2.5 solar masses, it can survive as a neutron star, supported by neutron degeneracy pressure and strong force repulsion. Above about 2.5 solar masses, nothing can stop the collapse. A black hole forms. The entire category of neutron stars occupies a sliver of mass between one collapsed state and another. They exist in a narrow window, balanced on a knife edge between the white dwarf regime below and the black hole regime above. A little less mass, and they would be white dwarfs. A little more, and they would be black holes. They sit precisely in the zone where quantum mechanics and the strong force are powerful enough to resist gravity, but only barely. Only just. Only by the narrowest of margins. This narrowness is not a coincidence. It reflects the fundamental constants of physics. The strength of gravity, the masses of neutrons, the behavior of the strong force at short range, the speed of light. All of these constants conspire to set the limits. If gravity were slightly stronger, the window for neutron stars would shrink. If the strong force was slightly weaker, the maximum mass would drop. The fact that neutron stars exist at all is a consequence of the specific values that nature's constants happen to have. Now, how do we actually measure these limits? How do we know that neutron stars have masses near 2 solar masses? How do we constrain the equation of state? We cannot visit a neutron star. We cannot send a probe to one. The nearest known neutron star is hundreds of light years away. And yet, in the past decade, observations have given us extraordinary tools to study these objects from a distance. The most powerful tool is gravity itself. Neutron stars in binary systems, orbiting another star or even another neutron star, betray their masses through their gravitational effects. By precisely timing the radio pulses from a pulsar, a rapidly spinning neutron star that emits beams of radiation like a lighthouse, astronomers can measure the orbital parameters with incredible accuracy. In some systems, the timing is so precise that relativistic effects become measurable. The orbits precess. Gravitational waves carry energy away, causing the orbit to slowly shrink. Time dilation affects the pulse timing. All of these effects depend on the masses of the objects, so by measuring them, you can determine the masses with extraordinary precision. Several neutron stars have been measured with masses near or above 2 solar masses. A pulsar measured at about 2.01 solar masses was confirmed over a decade ago. Another pulsar was measured near 2.08 solar masses, making it one of the heaviest known. These measurements are critically important because they set a lower bound on the maximum mass. Whatever the true equation of state is, it must be able to produce neutron stars at least this heavy. Any theoretical model that predicts a maximum mass below 2 solar masses is ruled out. This single observational constraint eliminates a large number of proposed equations of state. It tells us the matter inside neutron stars must be quite stiff, meaning it must produce a lot of pressure at high densities. Then came the gravitational waves. On August 17, 2017, the LIGO and Virgo detectors observed something unprecedented. Gravitational waves from 2 neutron stars spiraling into each other and merging. This was the first time gravitational waves from a neutron star merger had been detected. The event was also observed across the electromagnetic spectrum, from gamma rays to radio waves, by dozens of telescopes around the world. It was one of the most thoroughly observed events in the history of astronomy. What the detectors picked up was astonishing. For roughly 100 seconds, the instruments recorded a rising chirp of gravitational waves as the 2 neutron stars orbited each other faster and faster, drawing closer together, accelerating toward inevitable collision. The signal grew louder and higher in pitch as the orbital frequency increased. In the final moments, the 2 stars were whipping around each other hundreds of times per second, each one deforming the other with tidal forces so strong that the stars were physically stretched like taffy before they finally crashed together and merged. Then the signal cut off. The 2 objects had become one, and the gravitational wave signature changed to something consistent with a rapidly settling remnant, possibly a brief hypermassive neutron star that then collapsed almost immediately into a black hole. Less than 2 seconds after the gravitational waves arrived, a burst of gamma rays reached Earth from the same direction. Then, over the following hours, days and weeks, telescopes across every wavelength band detected light from the aftermath. Infrared telescopes saw a glow called a kilonova, produced by the radioactive decay of heavy elements forged in the merger's debris. For the first time, astronomers watched the universe create elements heavier than iron in real time. Gold, platinum, uranium. These elements were being synthesized in the expanding cloud of neutron-rich material flung outward by the collision. The periodic table's heaviest entries were born in the wreckage of two colliding neutron stars. But for our story, the most important information was encoded in the gravitational wave signal itself. That tidal stretching we just described, the way the two stars deformed each other in the final moments, was not just dramatic, it was diagnostic. The amount of deformation depended on how stiff or squishy the matter inside the stars was. A stiff equation of state, one where the matter strongly resists compression, would make the stars harder to deform. A soft equation of state would make them squishier, easier to distort. This deformation affected the gravitational wave signal in a measurable way. By analyzing the precise shape of the gravitational waves, scientists could extract a quantity called the tidal deformability, which measures how much a neutron star deforms under tidal forces. This gave a direct observational constraint on the equation of state. The results indicated that neutron stars are not extremely stiff, but not extremely soft either. The matter is moderately compressible. This immediately ruled out some extreme models and narrowed the range of possible equations of state. Another powerful tool is an instrument called NICER, which stands for Neutron Star Interior Composition Explorer. NICER is an X-ray telescope mounted on the International Space Station. It measures X-ray emissions from the hot surfaces of neutron stars with extraordinary precision. By analyzing how the X-rays are affected by the star's gravity, by the bending of light near the surface, by the Doppler shifts from the star's rotation, scientists can determine both the mass and the radius of individual neutron stars. Knowing both mass and radius for the same star is incredibly valuable. The mass tells you how much matter is there. The radius tells you how much that matter has been compressed. Together, they give you a point on the equation of state curve, density and pressure at that particular mass. Multiple measurements of different neutron stars at different masses map out the curve. NICER has measured several neutron stars, and the results are placing tighter and tighter constraints on what the equation of state can be. What these observations are telling us is fascinating. The equation of state appears to be relatively stiff at moderate densities, meaning the matter pushes back hard against compression. This is consistent with strong repulsive nuclear forces at short range. But at the highest densities, the situation is less clear. There may be a softening at very high density, which could indicate a phase transition, perhaps the appearance of hyperons or the deconfinement of quarks. Or the equation of state may remain stiff throughout. The data are not yet definitive, but every new observation narrows the possibilities. Future gravitational wave detectors will see more neutron star mergers. Each one provides new data. Each one constrains the equation of state further. Next-generation detectors planned for the 2030s will be sensitive enough to measure tidal deformability with far greater precision than current instruments. They may be able to detect signatures of phase transitions inside the merging stars. They may be able to tell us whether quark matter exists in neutron star cores. There is something profound about what is happening here. For decades, the interior of a neutron star was purely theoretical. We could model it, simulate it, argue about it, but we could not observe it. The densities involved are unreachable in any laboratory. Even the most powerful particle accelerators on Earth, which smash nuclei together at enormous energies, create conditions that are hot and fleeting, lasting for tiny fractions of a second. A neutron star's core is cold and stable, persisting for billions of years. The conditions are different. The physics is different. And for a long time, we had no way to peek inside. Now we can. Not directly. We still cannot see through the crust to the core, but the mass, the radius, the tidal deformability, the gravitational wave signature, all of these observables carry information about the interior. They are like the sound of a bell telling you about its shape and composition without having to cut it open. The neutron star rings with information, and for the first time in history, we have instruments sensitive enough to hear it. Let me step back now and consider what we have learned across this entire journey. We started with a paradox. A dead star, no fusion, no heat engine, no radiation pressure, nothing that classical physics would recognize as a source of support, and yet it does not collapse. Where does the pressure come from? The answer, as we have seen, is layered. It is not one thing. It is several things working together, each dominant in different regions and at different densities. At the most fundamental level, neutron degeneracy pressure provides the backbone. The Pauli exclusion principle forbids identical fermions from sharing quantum states. In the incredibly dense environment of a neutron star, this means neutrons are forced into higher and higher energy states, generating an outward pressure that exists independently of temperature. This pressure is eternal. It does not fade. It does not require fuel. It is a feature of quantum mechanics itself, as permanent as the laws of physics. Layered on top of degeneracy pressure is the repulsive core of the strong nuclear force. When neutrons are pushed to separations below about half a femtometer, the strong force switches from attractive to repulsive, creating a hard wall that resists further compression. This stiffens the equation of state and provides additional support beyond what pure degeneracy would offer. Deeper inside the star, the precise sources of pressure become uncertain. Exotic particles may appear. Quarks may deconfine. Strange matter may form. The equation of state in the innermost core remains one of the great open questions in physics. But whatever is happening there, it is producing enough pressure to sustain observed neutron stars at masses up to, and possibly beyond, 2 solar masses. And all of this pressure has a ceiling. General relativity couples pressure to gravity, creating a feedback loop that ultimately dooms any neutron star above the Tolman-Oppenheimer-Volkoff limit. Above roughly 2 to 2.5 solar masses, the internal pressure cannot keep up. Gravity wins its final victory. The star collapses to a black hole, and matter as a meaningful concept ceases to exist within the event horizon. The neutron star, then, is not just a dense object. It is a battleground, a place where the deepest principles of physics are locked in a direct confrontation with each other. Quantum mechanics says particles cannot be compressed into identical states. The strong force says nucleons cannot be pushed past a certain proximity. Gravity says mass curves spacetime, and that the curvature only grows as matter is compressed further. General relativity says pressure itself adds to the gravitational pull. These principles are not in gentle tension. They are in violent, immediate, physical conflict, and the neutron star is the arena where that conflict plays out. The fact that neutron stars exist at all is a statement about the balance of forces in our universe. They require gravity to be strong enough to crush atoms and convert matter to neutrons, but not so strong that it overwhelms quantum pressure entirely. They require the strong force to have a repulsive core at short range, providing additional stiffness. They require the Pauli exclusion principle to hold absolutely, without exception, under the most extreme conditions imaginable. If any of these features of our universe were slightly different, neutron stars might not exist. They might all collapse directly to black holes, or they might never form at all. Consider for a moment what it means that a quantum mechanical principle discovered by studying electron configurations in atoms turns out to be the force that prevents stellar mass objects from collapsing into singularities. The Pauli exclusion principle was formulated to explain the periodic table. It was a rule about atomic structure, about why elements have distinct chemical properties. And that same rule operating at densities 100 trillion times greater than anything on Earth, holds together objects containing more mass than the Sun. The physics of the very small governs the fate of the very large. The rules that give you chemistry also give you neutron stars. Or consider the strong nuclear force. It was discovered through studying radioactivity and nuclear reactions. It is the force that powers the Sun, that makes nuclear weapons possible, that binds the protons and neutrons in every atom of your body. And that same force, through its repulsive behavior at very short range, provides a critical component of the pressure inside a neutron star. A force studied in laboratories using particle accelerators and nuclear reactors operates at cosmic scales inside dead stars scattered across the galaxy. Or consider the Heisenberg uncertainty principle, which we met earlier when it explained why confining fermions forces them to move faster. That principle was formulated to describe the behavior of subatomic particles in controlled laboratory settings. And yet, it is operating right now, at this moment, inside every neutron star in the galaxy, forcing neutrons into high-energy states that generate the pressure keeping those stars from collapsing. A rule about measurement and uncertainty at the quantum scale is holding up objects more massive than the Sun. The bridge between the quantum and the cosmic is not metaphorical. It is structural. It is load-bearing. Without it, the star falls. There is a unity here that is almost breathtaking. The same handful of physical principles explain phenomena across scales ranging from subatomic particles to stellar remnants. The quantum mechanics of fermions, the behavior of the strong force, the geometry of space-time as described by general relativity, these are not separate stories. They are one story. And the neutron star is where they all come together in the most dramatic possible way. We live in a universe where matter has a last stand, where the constituents of reality, the particles and forces that make up everything, engage in a final resistance against the most extreme gravitational compression the cosmos can produce, short of a black hole. That resistance is not powered by fire or fuel. It is powered by identity, by the quantum requirement that fermions remain distinct, by the nuclear requirement that particles maintain a minimum separation, by principles so deep they are woven into the mathematical structure of reality itself. A neutron star is the most extreme expression of matter's refusal to be erased. It is the last object before the void. The final form that matter can take before gravity strips it of all structure, all identity, all physical existence. Inside a neutron star, matter has been pushed to its absolute limit. Atoms are gone. Nuclei are gone. The familiar world of chemistry and elements and materials is gone. What remains is a quantum fluid of neutrons, possibly hyperons, possibly free quarks, compressed to densities that exceed the nucleus of an atom. And that fluid pushes back. Not because it is hot, not because it is burning, but because the laws of physics will not allow it to be compressed further without a fight. That fight is the pressure. That pressure is what holds the star together. And if you add enough mass to tip the balance, if gravity finally generates more pull than the matter can resist, the fight ends. The matter vanishes behind an event horizon, and a black hole is born. Somewhere in the galaxy right now, there are neutron stars spinning hundreds of times per second, broadcasting beams of radiation across light years, their surfaces glowing with the residual heat of their violent births. Inside each one, at this very moment, quantum mechanics and the strong nuclear force are doing what they have done since the star was born, pushing outward, resisting, holding the line against a gravity that never stops pulling. They have been doing it for millions or billions of years. They will keep doing it for trillions more. The fire is long dead. The fuel is long spent. But the pressure endures, because it was never about fuel. It was never about fire. It was about what matter is at the deepest level. And what matter is at the deepest level is something that refuses to be erased. That refusal is written into the quantum rules of the universe. It is as old as physics itself. And it is the reason that between the white dwarf and the black hole, in a narrow window of mass and density and pressure, there exists one of the most astonishing objects nature has ever created. A ball of neutrons the size of a city, heavier than the sun, held together by the deepest laws of reality, balancing on a knife edge between existence and oblivion. A neutron star. The last stand of matter against the force that shaped the cosmos.